Hello. In this video, we are going to discuss an example on bolted joints. Okay, this is part of the course Design of Steel Structures offered under the BTech Civil Engineering degree program of APJ Abdul Kalam Technological University in the 7th semester. Let us begin with the question. As you can see in this problem, the reference Indian Standard Code is IS 800 2007 version. So the problem stated is two plates 20 mm thickness are connected by a lap joint using M20 bolts of 4.6 grade. Fe 410 grades steel plates are used, and we are being asked to find the strength and efficiency of the joint. It is also indicated that the width of the plate is 180 mm, both the plates. So along with the problem, a sketch is also given, and you can ignore this blue and green writings because which I have included, but otherwise this is the sketch which is provided along with the problem. So as you can see, two plates which are lapped one over the other, and there are 6 bolts provided to join these two plates. Thickness of both the plates are 20 mm and width of both the plates are 180 mm, and edge distance is also given. As you can see, edge distance provided is 35, and this is gauge, which is the distance perpendicular to the direction of action of the force. This is the direction of action of force. So gauge is 55, okay, and pitch is 60. The lap distance is 130 mm. So this is the problem, and let us begin by listing the items which are given and writing the inferences as well as the assumptions. So the nominal diameter of M20 bolt is 20 mm. Hence we can find out the bolt hole diameter from table 19. Tolerance is 2, so the bolt hole diameter is 22 mm. Minimum edge distance, assuming that the edge of the plates are planed, the equation is 1.5 D0 as per clause 10.2.4.2. minimum requirement is 33 mm. What we have provided is 35 mm, or what is provided in the problem is 35 mm, and minimum pitch required as per clause 10.2.2 is 2.5 times diameter of the bolt. As you can see, the required is 50 mm, and minimum pitch among the gauge and the pitch, the minimum value is 55, so which is satisfactory. And let us continue with the ultimate tensile strength of the plate. As you can see, we are being given that we are using a Fe 410 plate, which means the ultimate tensile strength of the plate is 410 Newton per mm square, and ultimate yield strength of the steel plate is 250 Newton per mm square. Further, since we are using 4.6 grade bolt as indicated in the problem, it means we are dealing with the bearing type connection, and also the tensile strength of the bolt is 400 Newton per mm square, and the yield strength of the bolt, which we are not using in the problem anyway, it is 60% of the tensile strength, which comes around 240 Newton per mm square. Further, in the calculation we will be using the partial safety factors. Okay, as you can see, the partial safety factor, there are partial safety factor for load as well as material. So load partial safety factors are indicated in table 4, and the material safety factors are indicated in table 5. So in this case, okay, we are not being given with any load, and hence we are not actually magnifying, we don't have to multiply or we don't have to use the partial safety factor for load, and whatever load we will be calculating in the end of this problem or in the form of the strength will be the ultimate corresponding to the ultimate load or the factored load. So here let us list the partial safety factor corresponding to the material, which is given in table 5. Gamma MB refers to the partial safety factor for bolt. Gamma ML refers to the partial safety factor for the material or the steel plate corresponding to rupture, and gamma MO is partial safety factor for the plate corresponding to yielding. Now, what are the different limit states applicable for this particular problem? So, as we have already learned, the limit state method progresses by identifying the different limiting states, that is different possibilities of failure of the member or the connection, and we will be calculating the strength corresponding to that, and we will be taking the minimum among those, and that will be the strength of the joint or the member. That is the idea. And in this problem we have the limit states, that is the shear capacity of the bolt, okay, then bearing capacity of the bolt, then tensile capacity of the plate, and block shear rupture strength of the plate. So let us begin with shear capacity of the bolt, which is evaluated as per clause 10.3.3. okay, as you can see, this is the equation for the shear capacity of the bolt, and VNSB is the net capacity which need to be divided by the partial safety factor, and along with that we need to multiply it with reduction factors for long joint, large grip and packing plate as per 10.3.3.1, 3.2 and 3.3. and here VNSP value is VNSP is indicated by the or calculated by the equation FUB by root 3 into NN ANB plus NS ANB ASB. So here, as you can see, NN refers to the number of shear plane where thread is included in the shear plane, and NS refers to the number of shear plane where thread is excluded from the shear plane. Okay, if you look at our problem, we have only one shear plane, one interface between the lap joint, one shear plane, and let us make an assumption that the shear plane lies on the threaded portion of the bolt, that is, the thread is included in the shear plane, which means since we have only one shear plane, that particular shear plane is under the condition that the thread is included in the shear plane. So which means NS becomes 0 and NN is equal to 1. Okay, correspondingly NN A and B refers to the net area of the bolt at the location of the thread, and ASB refers to the area of the bolt at the location of the shank. Okay, so ASB can be calculated using the equation pi by 4 into d square, where d is 20 mm, and A and B, there are possibilities by which we can identify the pitch at the location of the thread or the depression at the location of the thread, and then corresponding to that we can calculate the actual net area at the location of the thread. But maybe possibly we can use an alternate equation, that is, we can consider that the area at the location of the thread is 78% of the area at the location of the shank. Okay, so with that assumption we can use the equation 0.78 into pi by 4 d square to calculate A and B. Okay, it is not very clear here, but understand that it is 0.78 into pi by 4 into d square, where d is 20 mm, and the value we obtain is 245.044 millimeter square. Substituting in the equation, we will get the value of VDSB as 45.272, and in our case, when we look at our problem, okay, we can understand that our problem does not fall in the category of a long joint or a large grip, and we don't have any packing plates. So maybe safely we can assume the value of beta LJ, LG and beta PK as 1. Hence there is no reduction required for the shear capacity of the bolt. The next one is, next we can calculate the design strength corresponding to the 6 bolts which is provided. Okay, so for all the 6 bolts the value will come around 271.632 kilonewton. Next, let us evaluate the bearing capacity of the bolt, which is calculated as per clause 10.3.4. See the equation where V and PB need to be calculated using the equation 2.5 into KB into D into FU by T. You can see that here T refers to the thickness of summation of the thickness of the plates which are stressed in the same direction. Okay, and definitely under the bearing condition, the bearing stresses will be acting in opposite direction for the two plates, and in the ideal case we should be taking the summation, we should take the summation of the thickness where the bearing stress is acting in one direction, and you should compare the two cumulative thicknesses, and the lesser one should be taken for the calculation of the bearing capacity, because our bearing capacity is directly proportional to T, and hence when T is less, the bearing capacity will be less. So we should be looking for the minimum capacity. So that's about T. Fu, ultimate tensile strength of the plate. D is diameter of the bolt. 2.5 is a constant, and Kb is a value which need to be calculated by evaluating four conditions. And first condition is E by 3d0, where E is the edge distance, and we know that in the problem the edge distance provided is 35 and the diameter of the bolt hole is 22. Then second condition, P by 3d0 minus 0.25. In our case the pitch provided is 60 mm. Okay, d0 diameter of the bolt hole is 22, hence we can calculate the or evaluate this particular equation. And then the third condition is FUB by FU, which is the ratio of ultimate tensile strength of the bolt to that of the material, and there also we will get the value. And finally the value of Kb can never be greater than 1. So whichever is lesser among all the four conditions will be taken as the value of Kb, and in our case it is 0.53, corresponding to the first condition. By evaluating, we will get VDB is equal to 173.84 kilonewton. Okay, and corresponding to the 6 bolts the value will be 1043.04 kilonewton. At this point I will also like to state that the bolt value, okay, for one particular bolt can be calculated at this point. That is, bolt value of one bolt is equal to lesser of shear capacity and bearing capacity. As you can see, we have already calculated the shear capacity of one bolt as 45.272, and here we have calculated the bearing capacity of the bolt as 173.84. lesser among these two is 45.272, which is the bolt value of one bolt. We will be using this in the subsequent steps. That is why I just wanted to mention it here. Then next in this state is tensile strength of the plate, which I have written as strength of the plate, which is actually tensile strength of the plate, and definitely it is the property of a tension member. So we will be looking at section 6, and we will be calculating it as per clause 6.3.1, and as per the calculation we have TDN is equal to 0.9 AN FU by gamma m, and here as you can see AN need to be calculated corresponding to the critical cross section where we expect the rupture. So this is important. So in our case we have a symmetric arrangement of bolts, and we can see that we have two bolt rows, okay, where there can be a tension rupture, and you have same number of bolts in both the rows, and it is actually symmetrical. Hence we can safely assume that the critical section of for tensile rupture will be at this particular location, or possibly at this particular location. Anyway, so let us assume this as the critical section for tensile rupture, and correspondingly we can calculate the value of the net area. So when you calculate, you can see that this particular part which refers to that inclination in the failure path, as we can see in our case there is no inclination in the failure path, and hence this part is 0. Here we need to substitute the value of B, N and D0, and finally we get net area of 2280. Correspondingly we will get TDN, or the tensile capacity of the plate, as 673.056 kilonewton. Next limit state we need to evaluate is the strength corresponding to block shear rupture, which is once again the property of the tension member. The plates acting as a tension member will be referring to clause 6, section 6, clause 6.4.1, and I have made a small change in the original calculation. So you can see that the failure path for the block shear rupture is indicated with this blue line. Okay, this center line is incorrect, and block shear rupture will not happen like that. Block shear rupture means the portion of the plate is actually separated as a block, and in this particular case there is a significant thing which we need to note, that is, though this portion of plate is separated from the main plate, a bolt is actually still intact between the two plates, which means the load which will be actually causing this block shear rupture will be, okay, the total load minus the load taken by this particular bolt. That is the theory. So which means when we are evaluating the block shear rupture strength corresponding to this failure path, we should actually add the strength of one bolt along with the block shear rupture, okay, in the other way. Okay, so that is why I have indicated it here. So once again let me state that the block shear rupture will happen along this blue failure path, and after the rupture we can see that one bolt is still intact connecting the small piece of the plate along with the together with the other plate. So which means the strength, okay, or the load which will actually cause such a failure, such a block shear rupture corresponding to this blue line, okay, will be the total load minus the load taken by this particular bolt. And in order to facilitate such a calculation, we need to include the bolt value or the strength of this bolt along with the block shear rupture strength calculated as per this failure path. Okay, that is what we are going to do. So you have two equations for block shear strength calculation. The first equation refers to a condition where our shear failure path is subjected to yielding and the tension failure path is subjected to rupture. So the line which is parallel to the action of application of the load, okay, is actually the shear failure path. These two are shear failure path, and this vertical line is the tension failure path. The tension failure path is necessarily perpendicular to the action of force, direction of action of force, and shear failure path is parallel to the direction of action of force. So with regard to this second equation here, the shear failure path is actually experiencing rupture and the tension failure path is experiencing yield. That is the difference between these two equations. So corresponding to the modification that I have made in the block shear rupture failure path, okay, I have made corresponding changes in the calculation also. As you can see, I changed 3 to 2 because initially as per this sketch there were 3 shear failure path, but as per my revised sketch there is only 2, and this is 35. Since it is not clear, I have once again written 35 over here, and similar correction is made for the calculation of AVN also. Then finally, while calculating TDB, as you can see, I have substituted all the values, and further the bolt value of one bolt is added along with TDB. So final TDB will include the bolt value of one bolt, this bolt, okay, and we are obtaining TDB as 934.148 kilonewton for the first case, and for the second case 968.449 kilonewton. So as I have already discussed, we have evaluated 4 different limit states, that is shear capacity of the bolt, bearing capacity of the bolt, tension failure of the plate, and or tensile strength of the plate, and block shear rupture strength of the plate. Among all these 4 calculations, we should be taking the least value, okay, as the strength of the joint. Why we are taking the least value? Because we might remember the saying, a chain is as strong as its weakest link. That is, a chain will break at the location of its weakest link, which means among the different limiting states which we have calculated, whichever is offering the minimum strength, the failure will be actually happening corresponding to that particular limiting state. So in our case, invariably it is the shear failure of the bolt. So corresponding to the 6th bolt, the value is 271.632. And finally, let us conclude the problem by calculating the efficiency of the joint. Efficiency of the joint is represented or is calculated with respect to the strength of the solid plate. Okay, as you can see, it is represented, okay, corresponding to the strength of a solid plate, where maybe if there was no bolt hole deductions because of the provision of the bolted joint, okay, it would have exhibited a strength corresponding to yielding. Again, it is evaluated as per section 6, that is yielding of the tension member, of the gross cross section of the tension member, and it is as per clause 6.2. So our efficiency is represented with respect to the strength of the solid plate. So the equation is strength of the joint divided by strength of the solid plate multiplied by 100. 100 is multiplied in order to represent it as a percentage. So as you can see, the value of TDG is calculated here, and with respect to the value of TDG, the efficiency is calculated, and we can see that it is 33.1997 percentage. That is, maybe you can round it off as 33.2 percentage. Hope you understood this problem. Thank you for your patient listening.